Earlier, when we looked at the planning graph, I already mentioned that there is something missing in this graph. There are certain nodes missing and there were certain edges missing. And that's what I said earlier, that there were no mutex relations included. So what we will do now is look at these missing nodes, and we will also look at the missing edges, which define mutual exclusivity between propositions and actions. So that's what we'll be looking at next, the mutex relation between propositions and actions. Earlier, we have looked at independence between actions in the same action layer. We have seen that two actions in the same action layer that are dependent cannot be included in our final layered plan. Now we will have a look of how this effect propagates through the planning graph, and first we will look at dependent propositions, and here is an example. This is part of the planning graph we have looked at earlier, and you will note that in the proposition layer P1 we have the propositions R2 and AR. That is, the robot R is at location 2 and container A is loaded onto the robot R. The proposition R2 is present in that proposition layer because it is a positive effect of the action MR12. The proposition AR is in that layer because it is a positive effect of the action LAR1. Now, you may remember these two actions from an example we have looked at earlier, and that showed that MR12 and LAR1 are not independent. So these are dependent actions, which means they cannot be selected from this action layer for our final plan. But of course, if these actions are the only reason why these propositions are in this proposition layer, and these actions cannot possibly occur together, that means the two propositions also can't possibly occur together, at least not in this proposition layer. So that means R2 and AR are incompatible in proposition layer P1. Another example would be to look at the propositions R1 and R2 in proposition layer P1. Clearly, these two propositions are a positive and negative effect of the same action. So if we include this action in our plan, we can't have R1 and R2 both be true in P1. So again, they are incompatible in this proposition layer. R1 and R2 are incompatible in proposition layer P1. So we have seen two reasons here why two propositions in a proposition layer may be incompatible. The first one, shown by this example, was that we had two dependent actions that are the only producers of the two propositions. Then the two propositions must also be dependent. And the second reason was that we had an action that had the two propositions we were looking at as positive and negative effects, and that again means they are incompatible in that proposition layer. Now we will look at how we can simplify this by dropping one of the two cases, namely the second case. And we can achieve this by looking at the things that were currently missing from the planning graph. And those are the no-op actions. So we introduce no-op operations for a proposition P, and we give those the name AP. And the purpose of these is that they carry forward the proposition P from one proposition layer to the next. So they have only one precondition, namely that the proposition P is true in the first proposition layer. And then they have one effect that makes the proposition true in the next proposition layer. That means in this example, we would actually need 6 additional actions in the action layer A1, one for each of these proposition symbols that we carry forward. So we have a no-op operation for each one of those. I want to look at only one specific no-op operation though, namely the one for AR1 that carries the symbol R1 forward. And now let's look at the same example we've just looked at in the second case of the previous slide, where we looked at the propositions R1 and R2 that were positive and negative effects of MR12. Now we can see that R1 is also a positive effect of AR1, and R2 is a positive effect of MR12. But when you think about it for a second, you will see that these two actions are not independent, so they cannot occur together in our final plan. And that of course means that the two propositions are incompatible in layer P1, but this time for a different reason, namely because the two actions that add them are incompatible. So the introduction of the no-op operations means we don't have to explicitly carry forward proposition limbles from one layer to the next, because the no-op actions do that for us, and they simplify our incompatibility test for propositions in the same proposition layer. Now that you've seen these examples, it should be fairly easy to understand the definition of what it means for two propositions to be mutually exclusive. So two propositions P and Q that are in the same proposition layer Pj are mutex, which stands for mutually exclusive, if the following two conditions hold. Firstly, every action in the preceding action layer, that's Aj, that has P as a positive effect, including the no-op operations, is mutex with every action in Aj that has Q as a positive effect. So if we find a pair of actions in the action layer Aj that have P and Q as effects respectively, and these two actions are independent, then we know that we can also have P and Q as propositions in the following proposition layer. And the other way in which we can have P and Q compatible in the following proposition layer is if there is a single action in Aj that has both P and Q as positive effects, or the other way around, if there is no such action, then the two propositions may be mutually exclusive. In other words, P and Q are not mutex if they are produced by a pair of independent actions or by a single action. I hope you understood this so far, because now I'm going to confuse matters slightly. So when I talk about independent actions, but what's actually written here in the definition is that we require the two actions in the same action layer to be mutex with each other. And that we haven't defined yet, but we will get to the mutex relation between actions shortly. Now, before we continue, here comes a little bit of notation, and I want to introduce the symbol mu pj for the set of all pairs of propositions P and Q, all those pairs, that are in proposition layer Pj and that are mutex. So mu pj are all the mutex pairs in proposition layer Pj. And for those of you who prefer algorithms to formal definitions, here is the pseudocode that defines mutex for propositions. Here we define the function mutex that takes three arguments. The first two are the two propositions in a proposition layer that we're trying to test for mutual exclusivity. And the third component is something we haven't seen, but as before, this is something we will see shortly. This is simply the set of all mutex actions in action layer Aj. Then we simply go through two nested loops here. The outer loop tests all the producers of our proposition P1. So there should be an action A1 that produces this proposition, and then the inner loop simply takes the actions that produce proposition P2. So we test all possible combinations of producers for the two propositions. And if we find a single pair, A1, A2, that is not mutex, that is not in our given mutex relation between the actions, then we can return false, because we know these two propositions can't be mutex. We found a pair of actions that can produce them, and these two actions are not mutually exclusive. Otherwise, if we can't find such a pair, then we return true, and we know that these two propositions in their proposition layer must be mutually exclusive. Now, you may ask, what happened to the second part in the definition, where we can have a single action that produces both? Well, this is actually covered by this algorithm when you select A1 and A2 to be the same action. Then it produces both the propositions we're looking at, and of course an action is never mutually exclusive to itself. So this case is covered with this simple algorithm. Now a quick word about the time complexity of this algorithm. And we see here that we have two loops over all possible actions. So if we assume that we have a maximum of m possible actions, including the no-op operations, then this algorithm will run in O of m squared, because we're going through two loops over all possible actions, and those are of course limited to all the actions we might have. So it's polynomial.